Differential calculus is a study of the rates of change, and we are going to demonstrate this using a simple linear relationship between y and x, where y is defined as x plus 3. In order to quantify this change, we need to have 2 points. So I'll make point I here and point F here, standing for initial and final. The change in x, delta x, would be here, and the change in y would be this. So delta x would be equal to x final minus x initial, and delta y would be equal to y final minus y initial. The rate of change, also known as the slope, would equal to delta y over delta x. Now, this is a linear relationship. If we were to have, for example, a quadratic relationship, so depending on where you put your point F and point I, let's say you want to put them here or here, the rate of change would not be the same. In these scenarios, we cannot use an interval to find our rate of change. Rather, we have to find the instantaneous rate of change, or the slope at a certain point. So if you were to zoom in to, let's say, this location, it would appear as if this point, or like this interval, was linear. This is where the concept of infinitesimal comes in. Basically, we want an infinitely small change in y in relationship to an infinitely small change in x. So dy is equal to the limit as y initial approaches y final of y final minus y initial, and dx is equal to the limit as x initial approaches x final of x final minus x initial. Now, if we were to plug this back into the slope equation, we would get dy over dx. And for simplicity's sake, I'm going to define y as f of x. So then dy would be equal to the limit of as x of I approaches xf of f xf minus f xi. Now let's define h as delta x. So h would be equal to xf minus xi. If we solve for xf, we'll find that it would be equal to xi plus h. Now we can redefine dy and dx. Since h is the difference between xf and xi, as xi approaches xf, h would approach 0, so dy would be equal to the limit as h approaches 0 of f. We define xf as xi plus h, so f of xi plus h minus f of xi. And we could also do this to dx. So dx will equal to the limit as h approaches 0 of xi plus h minus xi, which would just be equal to h. So now we can define dy over dx in terms of one limit. So it would equal to the limit as h approaches 0 of f x plus h minus fx over h. Let's apply this to a simple quadratic equation, y equals x squared. Let's say we're trying to find the slope when x is equal to 5. So we would evaluate this equation, limit as h equals to 0. And since we know that y is equal to x squared, we could simply plug in the equation here. So it will be x plus h squared minus x squared over h. We know that x is equal to 5 since we're trying to evaluate it at 5. So then it will be the limit as h goes to 0 of x plus h squared is x squared plus 2xh plus h squared minus x squared over h. Now x squared and minus x squared is 0. H and h cancel out, and you would get two x plus h. Since we know that since we're trying to find when the limit of h approaches 0, h will just be equal to 0, and it will be equal to 2x, so the slope when x is equal to 5 is actually equal to 10.